This is section 6.1, part C, continuous random variables. When we use the table of random digits to select a digit between 0 and 9, the result is a discrete random variable called x. The probability model assigns probability of 1 out of 10, to each of the 10 possible values. So below is a probability distribution. So if you remember back to those random digit tables, there are only possibilities, if you're doing one-digit numbers, of getting a 0, a 1, 2, all the way up to 9. It's not possible to get a 1.3. So this is why that would be a discrete random variable. Suppose that we want to choose a number at random between 0 and 1. This is allowing any number between 0 to 1 to be an outcome. Calculator and computer random variable generators will do this. The sample space of the chance process is an entire interval of numbers, so our sample space S contains all numbers between 0 and 1. Call the outcome of the random number generator Y for short. We can find the probability of an event like the probability that Y is between 0.3 and 0.7. As in the case of selecting a random digit, we would like all possible outcomes to be equally likely, but we cannot assign probabilities to each individual value of Y and then add them together because there are infinitely many possible values. In situations like this, we use a different way of assigning probabilities directly to events as areas under the density curve. Remember, we talked about the density curve in Chapter 2. So to do this, we are going to have to find the shaded region. So the probability of a random number generator producing numbers Y that are between 0.3 and 0.7 would be 0.4. That's because the area of the shaded rectangle is length x and it's length times width. So our length would be 0.4 and our height or our width of this would just be a height of 1. So 0.5 times 1 would just give us an area of 0.4. A continuous random variable, x, takes all values in an interval of numbers. The probability distribution of x described by a density curve. The probability of any event is the area under the density curve and above the values of x that make up the event. The probability distribution for a continuous random variable assigns probabilities to intervals of outcomes rather than to individual outcomes themselves. So you need to be cautious. All continuous probability models assign probability 0 to every individual outcome. Only intervals of values have positive probabilities. We can use any density curve to assign probability. The density curves that are most familiar to us are the normal curves. So let's do an example that is a 4-step process. Remember, if we're talking about the normal curve, this means we are talking about our z-score. So we are going to find our z-scores again and use our tables from those. So the height of a young woman closely follows the normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. This is a distribution for a large set of data. Now choose a young woman at random, call her height y. If we repeat the random choice very many times, the distribution of values of y is the same normal distribution that describes the height of all young women. Find the probability that a chosen woman is between 68 and 70 inches tall. So the first thing we need to do is we need to come up with our state, or what question we're trying to answer. So for our state, we can say, what's the probability that a randomly chosen young woman has a height between 68 and 70 inches? Remember, next comes the plan. So we need to describe what we are going to be doing. So our plan for this problem is that the height y of the woman we chose has a normal distribution of 64 inches as the mean and 2.7 inches as the standard deviation. We want to find the probability that y is between 68 and 70. We will standardize the heights, which means we will find the z-scores, and then use Table A to find the area under the curve. So for the do, the first thing we're going to do is we will find the z-scores. You will have two different z-scores. Remember, z is equal to x minus mu over sigma. So we have two different x values right now. We have an x value of 68, and we have an x value of 70. So we're going to find a z value for both of those separately. So we're going to do 68 minus 64 divided by 2.7, and that's going to give us our first z-score of 1.48. To find the other z-score, we're going to do 70 minus 64 over 2.7, and that will give us a z-score of 2.22. Now we need to find the areas under these. Now remember, when you're looking at your table A, if I have a z-score of 1.48, the table is going to tell you the area to the left of that. And if I have 2.22, the table will tell me the area to the left of that. We want to find the area that is between those two values. So if we find both areas, we can then subtract them. So looking at the table, we know that the probability of getting a z value that's less than or equal to 2.22 is 0.9868, and a z-score of 1.48 will give us an area of 0.9306. To find the area between those two, we will subtract them, and we will find that the probability that the woman is between 68 and 70 inches will be around 5%. So now we need to make our conclusion. So we will conclude that there is about a 5.6% chance that a randomly chosen young woman will have a height that is between 68 and 70 inches. When you go to take your AP exam, when you solve problems involving random variables, start by defining the random variable of interest. For example, we let x equal the APGAR score for the baby selected in previous sections. In this section, we let y equal the height of a randomly selected young woman. Then state the probability you're trying to find in terms of that random variable. So then we're looking for the probability that 68 is less than or equal to y, which is less than or equal to 70, or the probability that x is greater than or equal to 7. But before you use those x and the y's, make sure you properly define what they are first.